Okay, good morning everyone. Today, as previously announced, we are going to, I'm going to introduce you the first assignment that is about the experimental modal analysis. I already uploaded on WeBeep on a dedicated folder that is within the assignment section a zip file that should contain the slides that we are going to look at today, together with the data you should use to work on the first assignment. Okay, I don't know if you already downloaded it, but I hope that everything is fine with that. So, what to expect from today's lecture? So, the idea is that up to this point, we always looked at the structure for which we would like to compute the modal parameters. Now we want to do something that is, in some way, the inverse of this procedure. So we already have a structure. We are able to measure some data that are representative for the vibrations of that structure. And by looking at those data, we wanted to retrieve information about the modal parameters of the structure. So it's the way, a different way to see the same problem, okay? And this is something that usually is very important from a practical point of view, because we have many structures that are already there, and it would be of interest to build some numerical model to be able to describe them, or just to analyze different loading conditions for which we wanted to know the modal parameters of those structures. So what we are going to do is to analyze some data that are representative for the motion or the vibration of an elastic model of a structure that is now under construction here in Milan, and that wind tunnel model has been tested in our wind tunnel a couple of years ago. And then, by looking at those, analyzing those data we are going to look at today, we can compare the outputs or the modal parameters we have been able to estimate with the one that are coming from the finite element model of the structure itself. Okay, so from this lecture, what I'm going to share with you is some basics about the experimental modal analysis that I'm pretty sure you already introduced with the professor on Wednesday, and then we are going to see how we can identify the modal parameters, then briefly introduce the experimental data I shared with you, and finally to say something about how to compare those data with the output you have from the finite element model. You already have the output, so in this case you don't need to run any finite element code. That instead will be the topic of the next lectures. So, as I was saying before, it could be useful for many reasons to extract some information about the modal properties of a structure from some measurements. And this is usually done for two different purposes. The first one is the so-called model updating. So you have a numerical model that typically is a finite element model of a certain structure, and you want to be sure that that model is really describing the behavior of the structure you have. So what you can do, that is something that we are going to do also during this lab, is to run the model and see the output you are getting and compare it with the one you got instead from the experimental data. So by measuring directly the behavior of the structure. The other way is the so-called model validation, that is slightly different in the sense that you work on your model, and in the end, by looking at the structure, let's suppose you have a certain frame here outside that we're doing some maintenance, and you want to build the numerical model of that frame. You look at that, you can see they have some beams with other additional beams. So you can insert or you can build an analytical numerical model that is representative for the properties of those beams. Then you run your model and you want to see if the output of your model is aligned with what you can directly measure for the structure. This is the so-called model validation. So you build the model on your own and you want to validate it with the experimental data. So those operations are something that usually are very useful to understand or to improve the capabilities of some numerical or analytical models. In this case, what we wanted to do is to be able to measure some behavior of the structure that is already there, and to be able to extract the modal information from those data. When we are referring to the modal information, usually we are referring to the natural frequencies, damping ratio, and mode shapes for each of the modes that can be extracted or that you could be interested in for your structure. So the parameters that usually we are always interested in are natural frequencies, damping ratio, and mode shapes. This one for each mode. We already saw how a certain mechanical system endowed with a certain mass distribution can be always analyzed relying on the modal approach. And so we know that the natural frequencies, the damping ratio, and the shape of the mode are something that are able to fully describe what is going to happen in terms of modal approach in your structure. How can we do that? In this course, we mainly focus on the so-called modal identification techniques for a single degrees of freedom system. And this is because the basic idea behind this assumption is that you can, in the neighborhood of a resonant mode, so if you are close to one of the natural frequency of the system, what you can do is to approximate the behavior of your structure with that specific mode, and that's it. So, at the beginning of the course, but even last week with by solving the exercises, we always stressed that if we have a certain structure, this structure has an infinite number of natural frequencies and so mode shapes. The idea is that if we are close to one of the natural frequency of the structure, instead of considering the infinite modes, we are going to consider just the resonant mode. That's the reason why we can rely on the so-called modal identification techniques for 1 degrees of freedom system. We have a structure that we know has an infinite number of frequencies, but if we are close to one of the natural frequency of the structure, we could approximate the response of the system with just one mode, that is the resonant one. So, if we go back to the basics behind the 1 degrees of freedom system, we already know that if we are referring to the free decay, so the free response of the system, we are going to expect a response of the system that is decaying in time due to the fact that we have some damping on that. And we already know that by looking at the properties of that decay, we could address or we could estimate the properties of this system. We know that the inverse of the period is the natural frequency of the structure. And we know that the way those amplitudes are decaying can be described with a negative exponential function in which the coefficient of alpha is directly related to the damping ratio we have in our structure. So, if we would be able to measure a decay of a certain structure, we could easily estimate the natural frequency and the damping ratio by just analyzing the decay. Which is the problem of a decay if we think about complex structures that could be even a pinhead beam? That is not that easy to select just one of the natural frequency. We know that as soon as we apply a certain initial condition to the simply supported beam or simply supported cable or whatever structure you want, in principle, all the modes are reacting. And so the characteristics of the decay we could get is something that cannot be directly related to the single mode. We saw during the third exercise together that if we are able to apply an initial condition that is coincident with a certain mode shape, in that case the response will be just driven by that modal contribution. If you go back to the exercise session in which we started with the simply supported beam and we applied both the boundary conditions and the initial conditions, at the end we mentioned that if we have the initial condition that in terms of position is coincident with the first mode, the response of the system will be driven by just one mode. So if you can do something like this, you could rely on the free decay response of the system to identify the modal parameters. But if you think a more complex structure, this is something that is not that straightforward. First of all, because maybe you don't know which is the shape of the first mode. And then because you should be able to apply an initial condition that is exactly matching that mode shape. So this is usually something that is not that viable for complex structure. It's easy if you can do that, but just looking at one decay, you have all the parameters you need, but this is not straightforward if you are dealing with a complex structure. So we need to move ahead and to rely on the forced motion of a system. To do that, we will just briefly recall some of the formulas that are behind the modal approach, just to be clear about the possibility to understand, to retrieve the modal information from the forced motion of a certain structure. So let's suppose that we refer to a very simple case, that is the inner beam. In the inner beam, if we know that we are going to describe the transversal vibration with W, we know that W should be a continuous function of x and t, as we saw up to this point in this course. And we know that through the modal approach, I could describe this response as a combination of a certain number of modes. This is something you should be familiar with. We always know that we could describe W as a combination of the mode shapes, and the way we are combining the mode shapes is something described by the so-called principal coordinates. If we have a certain force applied on that, and usually we are considering an harmonic force, supposing that this location is xk, we know that the external force can be described through the modal approach as a Q force that for the mode I can be written as Q0I times the tendency, and the amplitude of this force, this Q0I, is something that can be described by relying on the principle of virtual work as the product between the force, F0, and the mode shapes computed exactly in that location. So the external force F of t will be described in the modal approach as a Q force that is for each of the modes you have in your structure, and this, through the Lagrange equation of the principle of virtual work, can be described as the product between the force F0 and the mode shape I computed in the location where the force is applied. If you proceed with the computation of the modal mass and the modal stiffness, and you account for the damping with the Rayleigh hypothesis, so combining the stiffness and the modal mass, you could obtain the equation of motion for the system in principal coordinates as mi star qi double dot of t plus ci star times qi dot of t plus ki star times qi of t equal to f0 phi I x of k times I capital omega t. This is the equation of motion of the 1 degree of freedom system in QI that is describing the behavior of the ith mode. If you are able to compute the response for each I, you can then go back to describe W. This is the basics of the modal approach. If we wanted to write this in a matrix form, what we should write is M star times Q double dot plus C star times Q dot plus K star times Q equal to the vector of Q0 times EI capital omega, where we are simply putting together all the equation of motions, and we already know that the M, C, and K matrices under certain hypotheses can be diagonal. All of them will be diagonal. Or at least for sure M and K and the C if you have just the structural damping that you can describe through the Rayleigh model. This Q0EI capital omega t is something that should be collecting all the different mode shapes computed in location xk, and then you have the time dependency. I would say very easy in the sense that we are adding nothing with respect to what we saw up to last week. At this point, what we wanted to do is to compute the response of the system. So, which is the way we can compute the response of the system? We could start from each equation of motion from the single degrees of freedom system, compute the response in terms of QI, and then go back to the physical quantities. How can we do that? What we can do is to start with the equation of motion. So again, mi star qi double dot of t plus ci star qi dot t plus ki star q of qi t equal to q0i capital omega t. For this non-homogeneous ordinary differential equation, the particular solution can be written as qi of t equal to q0i ei capital omega t. So you could substitute this within the equation of motion, and so what you are going to obtain is minus capital omega squared times mi star plus imaginary unit times capital omega times ci star plus ki star, that is multiplying q0i equal to capital Q0i. At this point, obtaining the response of the system in terms of QI is very easy, because what we could do is to say that the QI is simply equal to Q0I divided by, here you can collect the modal mass, so you have M I star that is multiplying minus capital omega square. What's wrong? Minus capital omega square plus the imaginary unit times 2hi times omega I times capital omega, and then you have plus omega 0 I squared. I have here introduced hi, that is defined as ci divided by 2mi star times omega I, and then you should know that omega I is the square root of ki star divided by mi star. What do we have here? So 1 divided mi star times minus capital omega square and so on. This is the frequency response function associated to the mode number I. If we remember that we don't have just qi, but we have a certain number of q, this means that the vector q can be described as the q0 vector times ei capital omega t. And so we have that here the q0 can be written as the matrix of the frequency response function times the vector for q0, where the matrix of the frequency response function, since we are in the modal approach and all the equations are decoupled, will be just the frequency response function of the first mode placed over the first diagonal up to the frequency response function of the n mode. And then you have the zeros all around. So you have just the main diagonal that contains the terms that are different from zero. We are just collecting in a matrix form the output of the modal approach. If we have, and we are able to compute this, we have everything to go back to the physical coordinates. Because if you look at this, we know the external force and we are able to compute Q0. Then if we know the modal parameters, we are able to compute H, the frequency response function, and so we are able to compute Q0. If we are able to compute Q0, we can compute Q of t, and if we know the principal coordinates, we can go back to the physical coordinates. So what you have now in the slides is the way you can just go back to the physical coordinates. So Wx of t can be just written as the combination between the phi x, the vector of the mode shapes times q of t. Specifically, if we are going to compute the response over the location xj, so we are interested in wxj of t, what we can do is to compute w in the location xj, that is equivalent to say that we are going to compute the vector of the mode shapes in the location xj. Now we know that this q of t can be written as phi xj times u0 vector times ei capital omega t. And then we know that this q0 can be written as the matrix of the frequency response function times capital Q0 times ei capital omega t. And then we know that this, again, can be written as phi xj times the matrix of the frequency response function times Q0 that we previously wrote as f0 times phi computed over xk, because k is the position of the external force. You have a transpose here, and then you have a times ei capital omega t. If we rearrange those terms, we can write it as first f0, that is a constant value, I mean it's a scalar quantity, times phi xj times h star, that is the matrix of the frequency response function, times fk transposed times ei capital omega. Why do we need to write all of those formulas? Because we want to highlight one thing. That is, if I'm going to measure the response of the system over a certain location, that in this case will be xj, and I'm applying a force over the position xk, if I know those two quantities, I must know how those two quantities are referred to the modal parameters that are contained within this H star matrix. What I wanted to do is to measure a force that I'm going to apply to a structure, to measure the output, so the way the structure is behaving, and by relying on those two information, I wanted to retrieve the modal parameter. So if we look at those expressions, it is equivalent to say, I can measure this, I can measure the external force I'm applying, that is equivalent to say, I know partially this term here, and the way, if I know those relationships, I can estimate what is within this H star matrix, that is the matrix of the frequency response function, that in turn depends on the modal parameters of the system. This chain must be very clear in your mind, because this is the way you should understand why, by knowing the input, so the force I'm applying, and the output, this is the way I can retrieve information about the modal parameter of the structure. Because, first of all, I have a combination of all of them here. This is not just one mode. Within this H matrix and within those two vectors, I have information about all the modes. What we want to do is to measure input-output, and from them to obtain information about a certain number of modes. So, in the slides, you have just the same expression I wrote here in the blackboard, and then you have also the way you can look at this in a matrix form. So, the first vector, that is the vector of the mode shapes computed in the location of the output, is the first row vector you can see there. Then you have the matrix of the frequency response function, that, as I showed here, is a diagonal matrix. And then you have the vector of the mode shapes computed over the input location. That is xk. What we can do is to switch from the product of those vector matrices to a summation of the different contributions. Since H is a diagonal matrix, what you have over the slides actually reduces to the product between the first component of the first vector times h1 star times phi 1xk. This one should be summed with the second contribution, that is instead just referred to the second mode. Here you should have H2, and then you have the second component here. So what we can do is to rewrite these products of matrices and vector as a summation of the different modal contribution. In the summation, each term is just dependent on one specific mode. You have no mixed term because of the index of the frequency response function that is diagonal. What is important about that summation then? The point is that if you introduced the so-called Cij coefficient, that is a coefficient that you have for each mode, that's the reason why you have I as apex, and then that is dependent on the location of the output and the input. If you introduce this coefficient and you call it as the product of the ith mode shape computed in the location of the output times the product of the same mode shape computed in the location of the input, you can rewrite this summation here as F0 times the coefficient Cij times the matrix of the frequency response, the frequency response function for the mode number I. Why it is important to highlight this coefficient? Because this coefficient will depend on the location of the input and the output. And this will be the only term that will be sensitive to the location of the input and the output. Because instead, H star I just depend on the mode you are looking at. At this point, the frequency response function, that is always the ratio between the spectrum of the output, the spectrum of the input divided by the spectrum of the output. Here can be easily obtained as the output, so W10-EX-ASSIGNMENT divided by the input, that is F0 di capital omega T. And this one can be just written as the same summation in which you have the coefficient Jki times the frequency response function. Or, if you want to explicitly write this as the product between ith mode shape computed in the location of the output times the ith mode shape computed in the location of the input times the frequency response function, that is 1 divided mi star, that is multiplied minus capital omega J plus the imaginary unit times 2hi times omega I plus omega I squared. long formula is everything you need. Because if we are going to measure the output and the input, so we know the force we are applying, we know the response of the system, the ratio of those two quantities can be directly written as a function of the modal parameters. Because in that part, you have just the modal parameters you are interested in, that are the natural frequency omega I, the damping ratio Hi, and then the component of the mode shape number I in the location of the output and the input. So you are able to refer input over output to the modal parameters. Which is the problem? The problem is that I have a lot of modal contribution over there. Because if you look at this, it is true that input over output are directly related to the modal parameters of the system. But it's also true that you have a combination of them. How can we make this combination not effective? What we could say is that let's focus on the neighborhood of one of the resonance frequency. If you look at the plot you have on the slides, this is the response of a 2 degrees of freedom system, and then you have the contribution of Q1 and Q2 that are the red and the yellow curves. And then you have the dashed curve that is the combination of the two. As you can see, if you focus on the neighborhood of the first red resonance frequency, it is okay to say that the black curve can be approximated with the red one, both in terms of amplitude and in terms of phase. So from this, what we can say is that if we are in the neighborhood of one of the resonance frequency, we can still rely on this relation here. But what we can do is to delete the summation and just focus on the resonance frequency. In this case, if we are able to compute and to measure the frequency response function, what we can do is to focus on the behavior of the system in the neighborhood of a resonant frequency and relate the behavior of the system to the modal parameters of the resonant mode. In practice, this means that I can describe this frequency response function that I'm going to measure, or better, to estimate from measures, and to say that this frequency response function can be described through this equation here. Our exercise is measure input, measure output, compute the frequency response function, and then by knowing that the frequency response function can be described as a function of the modal parameters, estimate the modal parameters. The point is that in the experimental modal analysis, we are going to measure, or better, to estimate from measurements G, I, K of capital omega. What we want to obtain from measuring or estimating from measures the frequency response function is to obtain Hi, omega I, and information about the mode's shape number I. Is that clear? We already have the frequency response function. We want to obtain the natural frequency, the mode shape, and the shape of the mode that is excited in the neighborhood frequencies. Once we know this, we can rely on the information I'm sure Professor shared with you on Wednesday. we already know that for a 1 degrees of freedom system, the frequency response function actually contains all the information we need. If we look at the amplitude, we already know that the location of the peak of the amplitude will be exactly over the natural frequency of the system, or slightly apart if you consider that you could have some damping in your structure. And if you look at the phase, what should be clear is that the phase should cross the pi over 2 or minus pi over 2 at the resonant frequency. So if I have the frequency response function and I'm focusing on the neighborhood of a resonant frequency, the location of the peak is representative of the natural frequency of the system. The phase that is crossing pi over 2 is representative for the natural frequency of the system. That's not it, because that's not all, because looking at the frequency response function, we do have information also about the amount of damping we have for that mode. The height of the peak is directly related to the damping you have. The higher the peak, the smaller the damping. Or if you look at the phase, the faster is the switch from minus pi to 0. So the more vertical it is, the branch in which you are crossing the pi over 2, the lower will be the damping. So by looking at the height of the peak through the so-called half power method, or by looking at the slope of the phase diagram by relying on the so-called phase derivative method, you can estimate the damping ratio you have for that specific mode. And what about the mode shape? We are not just interested in the estimation of the damping ratio and the natural frequency of the system. That can be very easily retrieved from the frequency response function. What we want to do is also to have information about the shape of the mode. First thing to say, I can get information about the shape of the mode just on the locations I have the sensors. If you look at this expression, it's obvious that you cannot have information except for position k and j if you measure the frequency response function by putting an input force on k and looking at the output on j. So the best that you can do by looking at one single frequency response function is to obtain information about two locations. If by applying a single force you are looking for the output, so for the response of the system in many locations, you can reconstruct the mode. The idea is that if you are going to excite the system like here, and then you have a set of accelerometers in several locations, you can get instant information about to reconstruct the mode by looking at the different positions you are monitoring the output, okay? So, usually, when you have to reconstruct the mode, you are not going to rely on just a couple of measurements. You are applying a certain force, and you are looking for the output in different locations. If you have more than one location that have been monitored, you will get more frequency response function, and specifically you will have a frequency response function for each output location you have, and so you can reconstruct the mode. How can we do that? We are always starting from the expression of the frequency response function. Yes, are we considering the frequency response function of the resonance mode? Yes, I mean, you will have a frequency response function that has been computed for a large span of frequencies. And then you will focus on the neighborhood of the resonance frequency for each of the modes you will be interested in. Because otherwise, you cannot say that the frequency response function can be approximated with the single mode contribution. And so it will be a mess because you will have many frequencies or many resonance frequencies or many modal contributions to consider at the same time. Okay. So if we look at the frequency response function, that for the mode number I is relating the position K, that is the position of the application force, with the location J, that is the location in which you are looking for the output, this can be written as phi ixk times phi ixj divided by the modal mass, and then you have minus capital omega square plus the imaginary unit times 2h I times omega I times capital omega plus omega I squared. So this is the equations representative for the frequency response function. What is going to happen if we are going to compute this in the resonance condition? Computing it in the resonance condition implies to select the value of capital omega that is matching the omega I, that is the natural frequency of the system. The numerator won't be affected by that operation because nothing is dependent on frequency. So you will have at the denominator, the first one will become minus omega I squared. The first term will be simplified with the last one. You have a sum of terms, the first and the last are the same. So here you will have imaginary unit. I'm using J for the imaginary unit just to not make a confusion with I, that is the pedex of the mode, okay? And the same will be on the slides, but I think it's pretty clear. Then I have 2 times HI, and then here I will have omega I squared. This is the frequency response function computed over the resonant frequency. First of all, we realize that this is a pure imaginary number. You have the imaginary unit here. If you want to look at it the usual way, you could multiply both the numerator and the denominator by the imaginary unit. This times this will be minus 1, so you can put a minus sign in front. And this is clearly a pure imaginary number. You have a set of real coefficients that is multiplying the imaginary number, the imaginary unit, okay? So the frequency response function computed in the resonance condition gives us a pure imaginary number. If you look at the way this pure imaginary number is built, you have the contribution of the ith mode shape on the location of the input force, xk. You have the contribution of the damping ratio and the natural frequency of the resonant mode, that theoretically you could have already computed by looking at the position of the peak and the slope of the phase diagram. You have the coefficient mi star, that is the modal mass associated with the ith mode shape, the ith mode. So, if you are in a condition in which you are applying a certain force over the position xk, and let's suppose that you have many positions over which you are monitoring the output. I hope you agree with me that independently from the frequency response function I'm looking at, so the specific J I'm looking at, the terms that are here highlighted in red will be equal. Because they will depend just on the mode I'm considering, and I can consider the same mode, and the location of the input force that is the same for all the positions. So by considering a different J location, actually this number will be always the same except for this contribution here. So it is equivalent to say that computing the frequency response function in the resonance condition is giving me a pure imaginary number that is dependent on the location of the output, scaled by a certain number that is common is common for all the location you have here. This is exactly what we need to define the mode shape. Because defining the mode shapes, it implies to define these phi I x j for different j locations. And one will say, okay, but if I don't have the modal mass, I cannot estimate this. But in practice, you can. Because we already know that this phi vector that contains the mode shape is described except for a constant. So who cares about that scale factor? If you extract let's suppose we are calling those locations 1, 2, 3, and 4. If you compute G1 and then you still have the same K, this one will lead you to phi I x1, because this is the output, times phi I xk times divided by the modal mass divided by 2hi omega I squared. And then you will have the minus also if you want to write it properly, and then the imaginary unit. The coefficient you have here in red will be exactly the same coefficient you will have if you consider J2K minus, then you will have the same coefficient here, and then you will have J. If you consider J4K, that is location number 4, minus PIX4, then you will have the same coefficient, that is the same for all, and then you have the imaginary unit. So the different frequency response functions computed over the resonance condition will give you different numbers, because what is changing is actually that coefficient here. If we wanted to estimate the mode shape, what we wanted to do is to estimate exactly this part. So, what we can do is to extract the imaginary part of the frequency response function computed in the resonance condition, and this will give us, if you extract the imaginary part of the frequency response function computed in the resonance condition, you will get the product of those two terms. Their ratio will give you information about the mode shape. Because it will be the mode shape amplified by the same coefficient. But who cares about the coefficient? I mean, in practice, we are always displaying the mode shape by saying that the maximum is equal to 1. Or the normalization doesn't care. So, computing the mode shapes implies to extract the imaginary part of the frequency response function computed in the resonance condition. What we have in practice is the frequency response function. What we don't know is the mode shape. So we can easily do this, and we will get a number that, considered together with all the others, will give us information about the mode shape of the system. Now, it should be also clear the reason why I was mentioning that when you want to estimate the mode shape of the system, usually you cannot rely on just a couple of sensors. Because if you are just one input and one output, what you could get is just one number that is not representative at all for a shape. If you know just this term, or the product of this with this, you cannot reconstruct the shape. To reconstruct the shape, you need at least one here and one here, as an example. But if you have an accurate reconstruction of that, you should need at least 4, 5, 6 sensors. In our case, we will have 202. Because the shape we want to reconstruct will be pretty complex. And so we need a lot of numbers to be able to reconstruct the shape. But in practice, what you have to do is that for each point you are monitoring, you compute the frequency response function over the position of the natural frequency, and you extract the imaginary value. Then you normalize everything by a common factor. Usually you would identify the maximum and say, okay, let's put the maximum equal to 1, and that scale factor can be applied to all, just to reconstruct the shape. Is that clear, the way you can get information about the mode shape, the ith mode shape, starting from a set of measured frequency response function? This very simple concept must be applied to something that is not that easy because you have lots of sensors. And you will have real data, so real data are not that ideal as the one you can see there. But still, everything should work. This is the object of the study. I don't know if you have ever been in City Life here in Milan, but if you have been there over the last 6 months or 1 year, you have for sure saw the construction side of the canopy. The canopy is this connection between those two different buildings is approximately 135 meters long, and is located closer to the City Life district. And what we have done is to study the effect of winds on that structure by building a so-called elastic model. I don't know if you have ever been to the wind tunnel. Have you ever been to our wind tunnel? Yeah, all of you? Okay, so I hope that someone mentioned that we have 2 different kinds of models in the wind tunnel that can be tested. The first one are the so-called rigid model. So everything is as stiff as possible, and usually you are just reproducing the external shape of the object you want to study. Or in other cases, you are relying on the so-called elastic models. Elastic models are I would say, very time-consuming to be designed and built, because what we expect and we want from an elastic model is that it is able to deform and to behave as the real structure, but in a scaled way. So everything in this model is scaled, and if we wanted to scale the behavior in terms of response, now you know that we need to take care about the scaled mass, the scaled frequency. And so the scaled natural frequencies you are getting from the scaled mass and scaled stiffness, and so you are getting the scaled frequencies for the structure. So everything is supposed to behave like the real structure, but in a scaled way. How can we be sure that the model we built and we designed is exactly the same or representative for the full-scale structure? We are going to perform or to extract the modal parameters of those structures and to compare them with the full-scale structure. If they have the same mode and the same scaled frequencies, because the frequencies won't be exactly the same, but we have a scale factor, we are sure that the way it behaves under windy conditions will be the same as we expect the full-scale behavior. So in practice, once we build a model like this, we need to apply the experimental model analysis to be sure that the behavior of this structure is representative for the behavior of the full-scale structure. The full-scale structure is not there because it is under construction, but we do have the finite element model coming from the designer of that structure. So we can compare what we built that has been designed. So, I mean, we want to be sure that what we have, that the numbers we have on our finite element model of that structure are the same as the one we are able to finally realize on in the wind tunnel. This is usually something very important because in practice you have some parameters that you are not able to control at all. That is, as an example, the structural damping. Structural damping is something that is part of the structure itself. So you can decide the mass, you can decide the stiffness, you can decide everything, but then the amount of damping, you can avoid some solutions that for sure will be source of damping. But then you have some inherent damping that will be still there. So it's very important to be sure that before starting any test in the wind tunnel, the elastic model is really compatible in terms of dynamic properties to the structure we are going to match. Okay. Otherwise, all the results you are getting from this are not really representative of the full-scale structure. The reason why we wanted to test this is because it's a really flexible structure, and if you look at the rendering I plotted here, you can see a set of columns or something that looks like columns that seems to sustain the roof of that canopy. Okay. And then if you look at the model we built in the wind tunnel, you can see no columns at all over the suspended part. And this is because those columns are not used for structural purposes. Because, and now you should be aware of these conditions, I mean, you have the canopy, and the canopy under wind action or any other kind of action could displace, okay? And if it is placing like this, the side that is going downward will cause some compressions over those columns. And you know that very slender beams with a compression load is not good at all because of buckling. And so those columns cannot serve with the for structural purposes. What they are used for is to embed some dampers to damp out the vibration of the system, but also to remove water that could be stored otherwise on the roof. So when it is raining, due to the shape of the coverings, some water is going to be stored there. And to facilitate that the water flow away, they made some path over the roof, and then it will be, going downward through the columns you have there. So the columns that you will see once they will complete it, remember that they have any structural role in the behavior of the structure. They will be just to embed some dampers, so they are going to put some dampers to damp out the vibration, or be used as channels for water to be removed from the roof. That's the reason why we don't have columns here. If everything that has a structural role in the full structure should be here, because otherwise you are changing the stiffness, okay? So in this case, since the columns won't play any structural role, the columns are not reproduced in the elastic model. Another thing that I think is important to highlight is that, as we know, boundary conditions are affecting the natural frequency of the structure. So particular attention must be always paid to a constraint. As you can imagine, constraint won't be exactly some clamp, because they will always allow some amount of displacement and rotations. So if you look at this, in this detail here, you can see the way the cables that are running over the covering of the canopy have been clamped through some elastic elements to give to the structure the real stiffness he has in the full-scale condition, okay? So when you are designing an elastic model, there is always a tuning phase in which you can adjust some small details to finally get the frequencies that are matching the expected natural frequency of the structure. I mean, there will be lots of things to say about the elastic model, but this is not definitely the topic of today's lectures. But just something that you could need to know is that usually when we are designing an elastic model, there are some scaling laws you have to follow. First of all is to choose the length scale you want to work on. In this case, it was 1/70, because the model should fit the wind tunnel. Our wind tunnel is pretty big. It's one of the largest in the world. And so we can work with this, I would say, pretty large scaling factor, because it's 1/70. In other cases, you can have scaling factor of 1/200, 300, 400. That means that the model is becoming small like this. In this case, we want to work with a pretty large model. Our dimension of our wind tunnel is allowing for that. And this also allows for the reproduction of certain details that will be important in the behavior of the structure. Once you choose this, since you are running an elastic test, what is going to happen is that the mass is scaled with the cube of that lambda L, and the stiffness instead is scaled with the square of the lambda L. If you think about that, the frequency is the square root of the stiffness divided by the mass, you can easily get that the natural frequencies of the system will be squared by the square root, will be scaled with the square root of the lambda square divided by lambda cube. That means the square root of 1 divided by lambda square. Okay, so all the quantities must be compatible. How we measure the response of the system? First of all, we need some sensors that are not affecting the measure themselves. So if we are going to put accelerometers that are going to be pretty heavy, this will affect obviously the stiffness and the response of the system itself. So we looked for the less invasive solution to understand what is going to happen to our structure. And the final choice relied on a vibrometer that is able, through a set of scanners, to monitor different locations of the structures. And this is what we are going to use to read the output. While the input force will be an harmonic force with a frequency that, an angular frequency that is varying in time, so that we can reconstruct the frequency response function. Some more details about the way we are generating the input. As I was saying, the input force is a swept sine signal, that is actually a sine wave in which you are varying linearly or logarithmically the circular frequency, and then you are applying the force to the structure, to a so-called shaker that is able, as finger, to ensure that the force is applied in the desired direction. Obviously, everything in this kind of scheme is working if you are able to apply an harmonic vertical force. So you must be sure that everything is applied, is an harmonic force applied in the vertical direction. And then we have a load cell that is able to measure the input force. So we have the shaker. The shaker is able to produce a certain vibration. Then we have the stinger, and the stinger is actually allowing for ensuring the input force to be applied in the vertical direction. And then we have the load cell that is measuring actually the force we are introducing in the system. So everything that you can see there allows us to define the f of t. The f of t is a sine wave in which the circular frequency is varying in time, so that we can span from 0 up to 150 Hz as input force. Output. We needed to measure the input, and now we know almost everything about the input, but now we need also to measure the output. As I was saying before, there are lots of possibilities to measure vibration on a structure. Usually accelerometers are very, very commonly used in much of the monitoring campaign you can see. The most, I think, monitoring campaign you can see outside. And this is because usually they allow for a good resolution of the response you can get. You are reading accelerations that you can integrate them to obtain displacement. I don't know if you have already taken some measurements course. I hope so. Yeah, so you should be many more expert than me about choosing the instrumentation when you want to perform a measuring campaign. In this case, we opt for a vibrometer. The reason why is, first of all, because we need nothing on the structure, so we can use lasers that are generated by the vibrometer itself, that is positioned, externally with respect to what you want to measure. Usually lasers are not always applicable in all the conditions you can think about. In the wind tunnel, we are in a protected environment, so everything is working well. And the vibrometer actually is measuring the velocity. And this is usually a balance between the resolution you can get at high frequency, that could be very small for if you are just measuring the displacement, or for the other way, if you wanted to get information about the low frequencies, usually accelerometer could be not that accurate. So in practice, vibrometer is measuring the velocity. What we did is then to integrate it to obtain the displacement. That is the way we are usually expressing the frequency response function. Displacement over the input force. What we did, we monitored, as I was saying before, 202 different points that are spaced on the surface of the canopy like this. So we measured the input, we measured the output through the estimator H1. We already computed the frequency response function. So what you have there is already the metrics of the frequency response function that are relating the input force to the vertical displacement of each node. We span over a pretty large frequency range, from 0 up to 100 Hz, but what you will focus on is just between 2 and 8 Hz, because the purpose is to estimate the modal parameters for the first 4 modes. Just to give you an idea, I plotted here the amplitude and the phase of a subset of the points that have been monitored, okay? Because all of them will be a mess, okay? But just looking at the amplitude and phase of the frequency response function, we can clearly highlight some features that, first of all, are shared by all the points that have been displayed here. That means that probably we have a certain mode that is exciting all the locations we are monitoring here. And we can look at very similar behavior to the ideal condition or the ideal frequency response function, both in terms of amplitude and phase. I think it's obvious to say that over this location, we expect to have the first natural frequency. If you look at both the amplitude and the phase, in the amplitude you have the peak. This is in logarithmic scale, so you have the peak there, and then you have that the sensors are split over 2 different conditions, that is minus pi divided by 2 and pi divided by 2. And you can see that the slope is more or less the same from above and bottom points. So clearly there we have a natural frequency. Then I think, and we could expect also to have a natural frequency over this location. The peak is not that well defined, and also the phases are not that in order as the first resonant peak, but still we have the passage over the pi divided by 2. And so on. So if you go ahead, you can clearly identify the location, at least the approximate location of the first 4 natural frequencies. Why are we interested over those range? Because, as I was saying at the beginning of the lecture, what we can do is to approximate the behavior of the structure with the resonant mode just in the neighborhood of the natural frequency. Considering a larger span will imply to have also the contribution from other modes. So what you have to do is, first of all, to look for the position of those peaks, because looking at the position of those peaks will give you information about the natural frequency of the first 4 modes. As you can see there, you have the frequency response function, and I also plotted with that the mean of the average, the mean of the amplitude of the frequency response function. And so in this case, it will be pretty easy to locate the red dots you can see there. the mean of the average, the mean of the amplitude has no physical meaning at all. And at least allow us to relate some background noise you may have over the amplitude and to easily locate the location of the peak. Okay. But in this case, I mean, it's just for the peak's identification, applying the mean of the absolute. So what you should look for is the location of the peak to identify the natural frequency of the system, half power or phase derivative method to estimate the modal damping ratio, and then reconstruct the mode shape by relying on the 202 measuring point. This must be done for the first 4 modes separately. So you start with the first one, you estimate everything with the first one, then you move to the second one, you get everything from the second, and so on. This is a suggested procedure that is not compulsory. You can do whatever you want, okay? The point is to be aware about what you did and to get the results that are making sense, okay? My suggestion could be, let's start by focusing on one mode by one. Focusing on one mode by one implies to consider, to compute the frequency response function and to extract the frequency response function computed over the neighborhood of the resonant frequency. That could be the yellow range I highlighted here. I made them in PowerPoint, so it's not that accurate, but the idea is that limit yourself to near the location of the peak. Over that position, you can select the frequency response functions that are located closer to the antinodal position. Which are the antinodal position? It's the opposite of the nodal position. The nodal position is when you have a node of a mode. What is a node of a mode? It's when you have no displacement. Antinodal is when you have the maximum displacement. Why we would limit ourselves to the locations that are closer to the antinodal position? Because the peak will be well defined. If we consider this case, and we think that this with these sensors is located exactly over the mid-span, since the mode shape of the second mode will be something like this, if I'm looking at the frequency response function that is located, let's call this location number 1, if I'm looking at G1K, the amplitude, I will see a peak for the first natural frequency. Because the first mode will be something like this, so it will be excited. Nothing over the second, because the second won't be excited at all. I mean, it is located over a node, and then I will have information about the third, and again, nothing about the fourth, because the fourth will have again a nodal position in the mid-span. So if I'm looking at the frequency response function to sensors like this, what I expect to have is something like this. So if I wanted to get information from the second mode, for sure I cannot look for a peak for the sensor located in a nodal position. While everything is located in the antinodal position, like the same sensor for the first mode, is something that is really useful to define the modal properties, because the peak will be very well defined. And so what you could do is to select the antinodal position. How could you select the antinodal position? You extract the frequency response function in the neighborhood frequency, you compute the amplitude, and you choose the first, I don't know, 20 points, 30 points that are within that. The one that will show the highest peak will be also the one the more useful to understand the modal parameters. Once you have those set of antinodal locations, you can average the frequency response function and pay attention to average it in the complex domain. Compute the average of the frequency response function. Why we could compute the average of the frequency response function? We could delete some background noise or measuring noise. And if you look at the expression of the frequency response function, averaging different frequency response function will imply that to have the same quantity within the brackets, because this will be always the same. So you are getting an average of the frequency response function, but you are not changing the modal parameters we want to investigate. Because the only thing we are changing is just x phi I in the location xj. So you can compute the average, but this won't affect the shape of the frequency response function. Looking at the average, the frequency response function for the FRF located in the antinodal position, you can extract the location of the peak, the slope of the phase diagram, or the half power method to get an estimation of the damping ratio. And then you can take back, reconsider back all the frequency response functions and extract the imaginary part of the frequency response function computed in the natural frequency you just obtained. With this one, and by applying a proper scaling, you can plot the results and compare them with the one you get from the finite element approach. This procedure must be repeated for each mode. So I think that in your code, you will have a kind of 4 cycle that is going through all the modes. You take the frequency response function, you extract the one closer to the antinodal position, you perform the average, you compute natural frequency and damping ratio, then you consider that the neighborhood still of the natural frequency, over the location of the natural frequencies, all the frequency response function to reconstruct the mode shape. This is the output you should compare your result with. So in one of the map file, you have the mode shapes that have been computed with the finite element approach. Pay attention that to be able to compare your results with the one you get from the finite element approach, you should normalize the mode shapes in between -1 and +1, otherwise the colors will be for sure different. And then, to be able to compare the frequencies, you should apply to the wind tunnel models, so the ones that are between 2 and 8 Hz, a scaling factor that is the square root of the lambda L, where lambda L is 1 divided by 70. If you look at this, the mode shape, the mode from the FEM have frequencies that are very, very small. We are looking for frequencies between 2 and 8. We must scale them to be comparable with the one we have from the full scale. This is a list of the provided data. You have the frequency response functions. You have the location of the measuring points. You have the output from the finite element model, and you have a connectivity matrix that is containing the information about the nodes of the finite element model. Together with those map files, I'm pretty sure I have uploaded also a script that is called students.m, in which you have some hints for the visualization of the modes. So you have the patch, the syntax of the patch you can use to visualize the shape of the mode like this. Okay, so if you run this, you can obtain this kind of shape of colored pictures for the canopy. What do we expect from you? So you should work out the items that are listed there and include the results in a very short report. Very short report means it must be complete with all the figures and everything you look at to obtain the results. It must be complete with the results themselves, so estimation of the frequency, estimation of the damping ratio, and the visualization of the mode shapes compared to the one we get from the finite element approach. And that's it, I think. And we are not that interested in a long descriptions. We are not going to read your reports before the exam. It's impossible. You are too many. You are 250, and we cannot read your reports before the exam. The delivery day of the report is the day of the exam itself. You are coming to the exam, we are looking at the report together. So mainly we are focusing on pictures. And this means that we can ask information about the way you get that picture, the way you estimated the mode shapes, the way you located the natural frequencies. Why did you average the frequency response function, okay? So we are not that interested in comments you may have written in the report, but mainly in what you understood and the way you did that assignment. You can have some comments on the report, of course. That could be also helpful for you when you are at the exam, but no one is going to read all the sentences you are putting in there, okay? So don't waste time in preparing a long report. We are not going to read that. But it must be complete. Complete, it means that it must contain everything that is listed over there. Some suggestions that are something I think I already mentioned. Remember to scale identify the frequency. So you located the frequency in the experimental data between the 2 and the 8 Hz. Before comparing them with the one from the finite element approach, please apply the scaling factor, otherwise they won't match anyway. They are always below 1 Hz and you are looking frequency between 2 and 8 Hz, they won't match at all. So apply the scaling factor before saying that they are not matching. And when you are estimating the mode shapes, obviously, as we stressed before, the information you can get from the experimental modal analysis is just about the 202 points you are monitoring. We are not monitoring any point in the canopy. We are just monitoring the output over the measuring locations. To be able to compare the results you get from the finite element model that instead are more or less a continuous surface or something that is much more refined than the 202 points, you can either plot, you have two ways. Relying on a description like this, where instead of having the color of the marker as red, you can color the marker with a certain color that is ranging between -1 and +1. So the color of the points is directly comparable with what you have instead from the finite element model. Or, and this is one way, this is okay, you can get, instead of a continuous surface like this, a set of 202 points, and the color you assign to that point is compatible with that color bar. You have that color bar, because in the script it is also specified which color bar we are using for this one. Otherwise, the other possibility is to interpolate the data from the 202 points, that is the one we are measuring, over the grid of points that is used by the finite element approach. If you do that, it's like you are extending the data from the 202 locations into the grid of nodes you are using for the finite element approach, and so you should get a surface that is comparable to this one. Okay, you can use that, but both the ways are okay. In principle, you are not obtaining any information except for the one you are getting from the 202 points. And finally, to be able to compare, please be sure that you are assuming the same normalization. When you are comparing a shape like this with a shape like this, if you are coloring them with the color map, one would say that they are completely different. But their shape in practice is the same. What we need to do is to apply the same scaling law. So the maximum can be equal to 1, and here the maximum can be equal to 1. In this case, if I get similar colors distributions and I'm using the same normalization, this implies that they are exactly the same shape. What my suggestion is to use a normalization that is looking for the maximum and is putting it as equal to 1, or is looking for the minimum and is putting it as equal to -1. What could happen is that the maximum is, I don't know, 100, and the minimum is -1000. In that case, it's the minimum that being higher in the absolute value than the maximum should be as equal to -1. Otherwise, everything will be with a negative sign will be saturated because you are fixing the maximum that is not that high. Okay, but you will realize it. I mean, it's something that is, I think, pretty obvious when you are trying to displace the results. Okay. I think that's it. This is my last lecture with you, because starting from next week you are going to to have Lawrence Lanzillo with you, that is, will take care about the finite element approach, and to introduce also the other assignment. But if you need any kind of help in this assignment, and I think you will, I mean, just because it's something that is pretty different with respect to what you are going to you have seen up to this point in this course, or generally speaking in your background, please write me. We can fix any kind of appointment or meeting or whatever. Unfortunately, I have to go back, but please don't be shy and just text me anything you need, okay? So thank you for your attention.